So question 2 exemplifies another kind of sort of terror tactic that they use, which is to suddenly introduce a kind of compound that you may well never have seen before, an epoxide. And the temptation is to think, oh, I don't know anything about those, I'm not going to be able to do this question, and and to panic. And there's absolutely no need. They will quite commonly do something like this, but what they will ask you to do is to use, in very, very simple reasoning, to just extend ever so slightly things you do know about, to sort of make predictions about things that you don't. So don't worry about it, just take it a step at a time, stay cool, and it will be no problem. Alright, so first of all, it wants an equation for formation of epoxy ethane starting from ethene. So it's going to be an addition reaction. You know that that's what alkenes do. So here is ethene, and here is epoxy ethane. So you can see that, as we expect in alkene reactions, all of the atoms that were there originally are still there in the product, and the only thing that's happened is that the double bond has gone, and in this case has been replaced just by a bridging oxygen like that. So you can see therefore that the addition is simply an addition of one oxygen atom, and because it's reacting with oxygen gas, that represents half an O2, and that's it. That's all you need for the equation. You can double it if you want to get rid of the half, but you don't need to. That's absolutely fine. And then it wants an equation for complete combustion of ethene. So complete combustion, remember, means that all of the carbons in the molecule end up as carbon dioxide. If you have incomplete combustion, which is what happens when there's not enough oxygen available to make that happen, is that you get carbon, which is soot, or carbon monoxide being formed instead. But in this case it wants complete combustion. So for burning equations I would usually tend to use the molecular formula, because all the structure is destroyed anyway, so it doesn't really matter about structural detail in this case. So there's ethane. It's going to be reacting with some oxygen, and it's going to form carbon dioxide and water. So it's just a balancing act then. So 2 carbons in ethene means you're going to get 2 CO2s. 4 hydrogens in ethene means you have to have 4 hydrogens here, which is 2 lots of H2O, and that just leaves this number to find then. How many O2s do we need to balance that up? So we've got 2 oxygens there plus another 4, makes 6 oxygens altogether on the right, so we need 6 on the left, which means 3 O2. That's it, job done. Okay, so now we come to this acid catalyzed hydration of epoxy ethane to make ethane 1,2-diol. And they give you this detailed mechanism, and again it looks very scary, and you think, I'm not going to be able to do this, there's all these complicated things going on that I don't know about. But it doesn't matter. When you actually get into it, the questions they ask about it are very straightforward. So the important lesson is, stay cool, take it a step at a time, and it will be fine. Okay, so the first thing it asks you to do is to just put the dipoles onto an epoxy ethane molecule. So here it is, and all you have to do is remember the story about electronegativity. Remember, carbon is much more electronegative. Electronegativity increases as you go across the period, as the nuclear charge increases. So oxygen is much more electronegative than carbon, and it pulls the electrons towards it, so it becomes delta negative, and the carbons become, both of them, delta positive, and those are the dipoles. Okay, then it wants to know about bond fission. No, it doesn't. It wants to know about curly arrows. So lots of curly arrows here, as there are in most mechanisms, and you have to just explain that they represent movement of a pair of electrons. Has to be a pair. If you just say movement of electrons, they're not going to give you a mark for that. Okay, then bond fission in step 2, so that's in this process. So it's this curly arrow that's representing fission. Remember, just means breaking. So it's this bond that's breaking, and what that curly arrow shows you is that the pair of electrons that form the bond, both of them go to that oxygen. This carbon gets none, and that's what heterolytic fission means. So the answer would be that when a bond breaks, both of the electrons go to one of the atoms and none of them go to the other one. That's all it means. Okay, how can you tell that water is acting as a nucleophile in step 3? So here is step 3, and you can see that what the water is doing in that step is using a lone pair of electrons to form a new bond to the carbon. In other words, it's acting as an electron pair donor, and that's what a nucleophile is. Okay, so because the water is donating a pair of electrons is the answer. How does the mechanism show that H plus is behaving as a catalyst? So the key idea about catalysts, remember, is that they participate in the reaction, but they're regenerated at the end, so that overall they're not used up. But by being involved, they provide a pathway with a lower activation energy than you would have if they weren't involved. So what you've got to look for is the step where the catalyst becomes involved, and then the step where it becomes regenerated, and just pick those out. So right at the beginning you can see the H plus becomes involved, accepts a lone pair from the oxygen. So that's the beginning of its involvement, and then right at the end in step 4 you can see that this bond breaks, pair of electrons goes onto the oxygen, and the hydrogen escapes as H plus, so the H plus is regenerated there. So all you have to say for your mark is because H plus is reacts in step 1 but is regenerated in step 4. Okay, now this next little question, it's only 1 mark, but it's a slightly more interesting one, because you do have to actually think a little bit, to figure out what's going on here. So it's asking what happens if instead of reacting with water, which is the reaction we've seen so far, it reacts with methanol. And again, because it's not a reaction you're meant to know about, what you have to do is to sort of do it by analogy. So this is the reaction we've had so far. There's our epoxy ethane, and we said that if that reacts with water, which we can write like that, then what happens is that we get, if we just draw the product out, so this is the reaction we've already been given, this is the one that's in the paper, then effectively the water just adds onto it, so you can see that the H adds onto there, and then you get OH added onto here. So the two ends of the water molecule, one adds onto the oxygen, one end adds onto the oxygen, and one end adds onto the CH2. So what we do is to think, well, probably the same kind of thing is going to happen when methanol reacts. So if instead of HOH we have HOCH3, okay, that's methanol, then just by analogy, without needing to think about the mechanism necessarily or anything as complicated as that, we just think, okay, it's going to follow the same pattern, so this hydrogen is going to go onto here, and the OCH3 is going to go onto there. Okay, so it's just following exactly the same pattern, so that would seem likely to be the structure of the compound, and if you add up the atoms involved, you've got 1, 2, 3 carbons, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens and 2 oxygens, which is what it says. Okay, so I like that little question. It was only 1 mark, but it's a good thinking question to have a go at. Right, question C. Why is ethane 1,2-diol much less volatile than oxygen? Remember, volatility has got nothing to do with reactivity. Volatility simply means how easy is it to vaporize. So what it's saying is, why is it harder to vaporize ethane 1,2-diol? And the obvious answer, so this is ethane 1,2-diol, remember, is that it's got 2 OH groups in the molecule, whereas ethanol only has 1, and therefore it can form more hydrogen bonds, so more energy is needed to break them when vaporization occurs. Okay, so more OH groups, therefore more hydrogen bonds per molecule, therefore more energy is needed to break them when it vaporizes, and that's your answer. Okay, so the next little bit is about esterification. So first of all, just let me remind you what the general pattern is for making a simple ester, and then we'll apply that to this specific instance. So here's ethanoic acid reacting with methanol. Remember, it needs conch sulfuric acid catalyst and heat. And the pattern of reaction that you need to remember is that you lose the OH group from there and the hydrogen from there. Okay, those get squeezed out to make a water molecule, and what's left, those two fragments join together to make the ester. So again, that's obviously not the mechanism, but that's the outcome, which is at this level all you need to know about. Okay, so you've got the OCH3 left over from the alcohol, this bit left over from the acid, and they join together to make the ester. So you need to be absolutely confident that you've remembered that pattern and practiced applying it to lots of simple ones. And then you're going to be able to apply it to this case, and the difference here, of course, is that ethane 1,2-diol has got two OH groups. And notice the key word in the question. It says ethane 1,2-diol reacts with excess ethanoic acid. When you see that word excess, remember it means more than enough to react with anything it could react with in the other molecule. So in other words, it's a hint that there may be more than one reaction in that particular, in ethane 1,2-diol molecule. The fact that it's saying excess ethanoic acid suggests it may react more than once. And of course the reason it can do that is it has not just one OH group, but two. So now we can just straightforwardly modify this mechanism, because now we're reacting not just with methanol but with this, and of course this OH group is going to be able to do exactly the same thing. So we can bring another ethanoic acid molecule in, like that, and pinch out a water in the same way, and so we'll get the CH3CO group added on and then at both ends, and we'll end up with this. So CH3CO and then OCH2 CH2O in the middle there, okay, which is what's left of the ethane 1,2-diol, and then CO CH3 at that end again. So that's your ester. That's actually all you need for the answer to the question. But if they wanted an equation, remember that this time you would have two H2O, because there's one produced from each of the esterifications. Okay, so that's that one. And then finally, it wants to know about oxidation with aqueous acidic potassium dichromate. So again, the issue here is that you've got two OH groups which could be oxidized. And the reason you can get several products is that they may not be oxidized to equal extents. So again, it's probably helpful if we remind you first of all what happens with a simple alcohol like ethanol, which is a primary alcohol, just like ethane 1,2-diol is. So there's ethanol, and remember that it oxidizes with aqueous acidic dichromate in two stages. First of all, if you react with the oxidizing agent, which you represent like that in an equation, remember, it oxidizes to the aldehyde, which is that, and produces water. So that's one possibility in oxidation, that wherever you have a primary alcohol group like that, it can turn into an aldehyde group. But remember then, if you oxidize for longer with excess of the oxidizing agent, then you can convert that into a different product, an extra oxygen on board, which is the carboxylic acid. So in ethane 1,2-diol, you have two primary alcohol groups, and they both of them can either oxidize to the aldehyde or oxidize further to the carboxylic acid, or of course one of them may not oxidize at all, and that's where you get this range of possible products. So it only asks you for two of them, which makes it quite easy, but again, set yourself, just by way of a revision exercise, the tougher challenge, which is to identify all of the possibilities. So this is our starting compound. With these questions where it's looking for lots of possibilities, I always tend to use skeletal formulae anyway, because I just find them so much quicker and easier. But particularly in questions like this where you've got to write out lots of things, then I think that's very helpful. So that's ethane 1,2-diol drawn skeletally. And obviously that's not one of the potential products, that's a starting material. But then you just say, right, let's start by oxidizing one end of the molecule. So the first product of oxidation would be to say, right, let's keep this end the same, but we'll oxidize that one to the aldehyde, so there's one of your possible products. Or we could oxidize that through all the way to the carboxylic acid, and there's the second possible product. And that's actually enough, of course. It only asked you for 2, so that would have been fine. Or we could oxidize this one to the aldehyde stage, and then have that one as well as the aldehyde stage, or that one at the carboxylic acid stage. So that gives you 2 more possibilities. Or we could oxidize this one through to the carboxylic acid stage and get that. So those are the possible structures you could have. Any 2 of those would do. So you could do it kind of by trial and error, but it's quite useful exercise to have a go at being systematic like that and think about what all the possibilities are. Okay, that's it for question 2.